Association. I am your host, Dulvan Dodan Malwar. To get us started, I would like to invite the chairman of the Royal College Science Association, Lakhindu Veerasinghe, to address the gathering.
Good afternoon. Dear Principal Sir, Mr. MVS Gunatilaka, Vice Principals, Senior Master in charge of Clubs and Societies, Mr. TDCP Amartunga, Senior Games Master, Mr. MM Rias, Lecturer for today's session, Professor Thrishantha Nanayakkara, teachers, prefects, my dear fellow royalists and all the participants. I warmly welcome you all to this special occasion. This online workshop series is called by the name of SCI-NEXUS. This project will help all the students to build their knowledge and their interest on various science fields. And also, this project will help them to build their career paths in their future. Today's lecture is on a topic called robotics, conducted by Professor Thrishantha Nanayakkara. Professor Thrishantha is a very humble man and a very experienced speaker who thinks and supports to build their educational science knowledge in the younger generation. And also, he is a famous lecturer at this relevant field. And we know that he is the best person to do this session for today. I hope you all know that RCSA is an educational club who always thinks about the development of the Sri Lankan school science education. And we hope you all know that we have done lots of projects to uplift the standards in our alma mater. So I will conclude my speech from wishing you a great and a knowledgeable day. Thank you. Over to you, Dulvan.
Thank you, Aya. Just a quick reminder that the lecture is live streamed on YouTube and the link for it is now in the meeting chat. මේ මතක් කිරීම මෙම වැඩසටහන YouTube ඔස්සේද සජීවී විකාශය වන බවයි. ඒ සඳහා link එක ඔබට chat එක තුල සොයාගත හැකියි. Now for the lecture. I would like to invite Professor at the Faculty of Engineering at the Dyson School of Engineering, Associate Professor in Design Engineering and Robotics at DSDE, Director of Morph Lab, Imperial College London, and the former Senior Lecturer of University of Moratuwa and King's College London. Please welcome Professor Thrishantha Nanayakkara. Sir, මෙතන සිට දේශනය පැවැත්වීමට ඔබටයි මේ ආරාධනය.
Thank you very much. Let me share my screen. Can you see my screen?
Yes, sir, we can see your screen.
Okay, thank you very much, and it's great to be here to talk to school students in Sri Lanka. It's always a pleasure and a privilege to do that kind of things from outside Sri Lanka. And congratulations to the Royal College Science Society for organizing this event, and then being very generous to share this with other students in Sri Lanka. So that's a good leadership activity. So I'm going to talk about robotics, and I'm generally going to talk about soft robotics, which is my field of work. And I will give some insights about what is happening in soft robotics these days, and then give some ideas about how you can continue work and studies in that area in the future. So robotics has a long history. It's the ideas came during the slavery time. Like this famous woman called Sojourner Truth. She was a slave, auctioned 8 times in her life. And then she gave a very famous speech, Ain't I a Woman, in Akron, Ohio in 1851. And then most of her poems when she wrote was used by President Abraham Lincoln for his abolitionist movement and then his talks. So Smithsonian Magazine names her as the 100 most significant Americans of all time. And then NASA, the first robot to be ever sent to space, they named that robot after Sojourner to respect her fight for freedom and in a struggle for freedom from slavery. So the analogy they gave was like Sojourner fought against social gravity, and then this robot, for the first time in man's history, will fight against Earth's gravity and then go to free space. So to symbolize that, like, so they named the first robot after her. And then artists like Karl Kopek, so they came in 1920s, and then they picked up these ideas and then envisioned a future of robots, right? So his famous stage drama called Rossum's Universal Robots got human actors to like wear and behave like robots. And then the idea was like, so through this stage drama, he wanted to project this futuristic idea that in the future, there will be machines that can do work the slaves are doing now, slaves were doing. And then we won't have to employ people in very hard, hazardous, toxic environments, and then the humans can do better jobs, and then have a better life, and then the society will be more equal, and then the robots will replace them to do this kind of dirty hard work, um, and round the clock, right? So that was his vision, and then projected through some kind of artistic way. And then people like Isaac Asimov, these early writers about science fiction, and then he further went on to stipulate some rules that these robots should obey. There were three famous rules, and then that was the basis for many scientific, sci-fi movies. I think if you watch I, Robot, you can see how that whole movie is based on this Isaac Asimov's rules. So today we have lots of different robots in the industry, and then the robotic industry is growing around 30% to 35% compound annual growth rate, and it is a multi-billion-dollar industry today. So in late kind of 1980s, the robots were like this, right? So the first appearance of robots were in the industry, assembly industry, and manufacturing industries. So these were rigid robots, and these rigid robots could be programmed to do very stereotyped, calibrated tasks. And then you cannot see many humans in that environment, because it is a dangerous area to go for humans. So these robots could cut metal, work in very noisy environments like high decibel environments, and where humans really cannot survive for a long time without getting injured. And then these robots work around the clock. And then this kind of companies who employed these robots won the race against the other companies who employed humans. And then as a result, there was this huge kind of uptake of these robots by the industry. So the point here is that um, there's a demand and supply driven uptake of robots, right? So people need objects, kind of products and services that are calibrated and manufactured according to standards. So it doesn't matter how many cars you are making, each car should have the same quality. So it is true that handmade items are expensive, but the handmade items are expensive when there's no huge need for calibration, right? So like hand looms are expensive, which is great, right? So these textiles, you can have a little bit of variation across different products, and which is giving a unique uh, kind of taste and texture to each item they are manufacturing. So that is great, right? But if it is a car or a, automobile, you have to be sure that these things are manufactured to some kind of a calibrated standard, and then that is why this was taken up in the car manufacturing industry and other assembly mass manufacturing industries more than the others. um, but there were drawbacks, right? So this is one example. So in these environments, objects move around, and then these calibrations fail sometimes, and then these robots have to survive with uncertainty. So this is a European Union funded project I was involved in. This was done in collaboration with lots of different European partners. The idea is, if a robot picks up something, and then if somebody moves it, or due to some reason that object moves around, then the robot should be able to recover, right? And then recalibrate itself quickly and then get the thing done. So this is like extending their intelligence a little bit. So what happens if the object is moved beyond recovery, right? So to a bigger distance where the robot either cannot reach or it cannot accurately calibrate. So another robot, buddy robot, can come and help them. So this is a more collaborative intelligence, and then another robot understanding the difficulty of his colleague robot, and then doing in a very response mode adaptive task. So this is um, how we push the boundaries, the state of the art. So this was a research project, but it was adopted in the industry. So this is the latest kind of incarnation of these robots. So these are called cobots. The cobots are collaborative robots, right? So it is purposely not called robots because these are collaborative robots, and then these joints are safe. So you can have humans working around them, and these robots can collaborate with humans and other robots, right? So then it allows humans to come in and then do more tailor-made kind of customized interventions, and then the robots can continue to do their work, and then they can easily recover from different uncertainties, right? So they have what are called serial elastic actuators. So you can see compared to the first video, this video shows humans working around robots. So this is really needed because this human touch is really important in any manufacturing task. Like they had to do ongoing quality assurance, quality testing. This man is coming to check if the robot has done the job right, and then they can do some certain interventions that the robot cannot do, or just help the robot, right, to recover things and then do the task better. So the advent of cobots, these collaborative robots, is radically changing the industry. So this is going beyond car manufacturing now to other fields like agriculture, food industry, where you cannot really expect things to be really well calibrated, right? So agriculture or food manufacturing, uh, warehouses or retail and home-based industries, that kind of things, right? So the idea is to have this robot, for example, this RS10 robot cost around about, $20,000, right? Which is the lower end of the average salary of a kind of untrained worker, right? So like a laborer. So laborer's annual salary, which is really, really low, right? So annual salary is the cost of a robot. So if that laborer was doing some, like nut fixing or like polishing or like mundane work, why not get this robot employed to do that work? And then you recover the cost of the robot in 1 year, right? So you were anyway paying the person $20,000. So this can appear to be that, like, these robots are replacing low-end workers. There's an ongoing debate about it. But the thing is, there are not enough workers to do this kind of job. So the industries cannot really depend on labor mobility to sustain manufacturing and agriculture. So most European countries, UK is experiencing that kind of problems. Like, this is not just agriculture, the strawberry pickers and apple pickers. There are not enough people to work in those industries. And recently we experienced a driver problem, right? So the truck driver problem. So that lack of people to work in those industries creates the demand for autonomous driving or cobots, right? So it is not like robots replacing humans, or creating joblesses, or taking human jobs. It is not really that, right? So it is that there are not enough people to work in those industries, and then the robots are coming to serve that demand. So that is something I really wanted to highlight. So these robots have, as I said, the serial elastic actuators, right? So there's basically there's a motor, and then it is connected with springs to the load, and then you can just push the robot. Like, the robot is not going to kind of push you back too much. So you can see that that lady is working alongside that robot, that KUKA robot, which is a cobot. And then she is feeling very comfortable to work around that robot, right? So she's not really scared about, like, she's not even looking at the robot. So the robot is helping her to pick things, and then placing things in the right orientation so that she can just do the final fitting or reorientation. And then this is massively increasing the efficiency of her work, because she doesn't have to lift heavy objects. The robot is lifting the objects, and then repetitive things, and then she is doing just enough work to get it done, that human touch, last bit of the human touch is done. So this is the state of the art. And then it is the laboratories like mine and other lots of laboratories across the globe who are pushing the boundaries of this technology. So it is our job. So lots of companies are being spun out every year from different universities. For example, Imperial College London has spun out at least 16 robotics companies so far, and then so it is continuing, right? So our research, at some point, like, we do fundamental research, and then at some point it comes to maturity, and then it goes out as a company, right? So this is one of my colleagues' companies called the Qbot company. So he, Professor Peter Child's company. So his robot is doing insulation underneath. Like, so there are lots of in UK elevated floor houses, right? So these houses are elevated from, there's a gap between the ground and the floor of the house for insulation purposes, or like heat and other problems. And then these are relatively old houses, and then they didn't have good enough thermal insulation. So this robot can go underneath those floors and then do a proper calibrated surface insulation. And then you cannot send a human underneath. So it is, the gap is so narrow, and then it is not a comfortable area to work in. And then the chemical they are using is not very good to be around a human. Like, so when it is in vapor mode or gas, right? So they are squirting that underneath to the floor, and then that creates some kind of insulation. So these kind of companies now, they employ more than 20 people. Maybe about a couple of years ago now, it must be more than that. So it is important to notice that the fundamental research we are doing leads to a maturity like this, and then companies come out, and then that adds to the economic growth rate of the countries that really invest in robotics research, right? So these turn out to be billions of dollars of income, right? So the soft robotics field is a fascinating field. I'm involved in that. My research is on soft robots. So the soft robots are mostly motivated by, inspired by soft animals like the octopus, right? So the octopus can have tentacles, and then these tentacles can be stiffened, and then they just do lots of
Tell them
various
that
different things under the sea
What is your happy
on this.
place?
So these soft robot
my happy
inspired
place
robots
is when
can
I'm with
do
people.
underwater
I am a
exploration
social
and then
robot,
even
and nothing
surgery.
pleases me more
On the
than
bottom
having a
left
fruitful
corner,
conversation
this is
with
a project
someone
I was
that makes us
involved in.
understand
Again,
and
a European
appreciate
Union
people.
funded project with
Don't tell them
lots of
that
12,
though.
12 different European
What
partners.
is your happy place?
And the idea is
My happy
to have
place
a
is when I'm
octopus
with people.
tentacle
I am
type
a social
robot
robot,
that
and
can be
nothing pleases
squeezed
me more
into the
than
body
having a fruitful
through a
conversation
narrow
with someone
trocar
that
port,
makes us
which is about
understand
a 12
and appreciate
millimeter
people.
diameter port.
Don't tell them that
It's
though.
a small cut, and
What
then
is your happy
we go
place?
through that and then do the
My
surgery
happy
and then
place
come out.
is when I'm with people.
I
I
mean,
am a
these
social
robots are
robot,
essentially
and nothing
safe
pleases
to
me
be
more than
inside the
having a
robot and the
fruitful
human
conversation with someone
body,
that
because
makes us
they can be
understand
squeezed
and
in, and
appreciate
then
people.
if you turn
Don't
off
tell
the
them that
power, it just
though.
becomes a rope, right?
What
So you
is your
just pull
happy
it out.
place?
My happy place is when I'm with
That
people.
front is
I am a social
advancing
robot, and
rapidly.
nothing pleases
And
me
then the
more than
Sophia
having a
is,
fruitful
Hanson
conversation with
Robotics in
someone
Hong Kong.
that
So
makes
this
us
kind of robots
understand
can have
and
intelligent
appreciate people.
conversations,
Don't tell
and
them
then
that
have
though.
very realistic kind
What
of
is your
facial
happy place?
expressions for humans.
My
And this
happy
can be
place is when
used
I'm with
for
people. I am a social robot, and nothing
therapeutic
pleases me more than having
interventions
a
to
fruitful
elderly
conversation
people
with
or
someone
people
that makes
who
us
are
understand
undergoing
and
kind of
appreciate people.
mental
Don't tell them
challenges.
that though.
So these are
What
coming up,
is your happy
right?
place?
So that kind
My
of
happy
emotional
place
engagement
is when
robots
I'm
are
with people. I
really
am a
rapidly advancing. So specifically, I'm working on soft robots. So for soft robot market, there's a projected to be about a 4 billion market by 2025, and it is the growth rate is about compound annual growth rate is about 40%, and then different market intelligence agencies predict it slightly differently, but they tend to agree that it is growing at 40% every year. So the hope is that uh, who are listening to this talk, you are school students, and then by the time you go to university and then come out of the university, maybe in about 4 years or 5 years time, you will be in a society with lots of opportunities in robotics, right? Lots of companies around and different opportunities to work. So the essential thing is that you need to be very good in mathematics. You need to be very good in physics. And then you need to know your coding, right? Software skills. So if you know mathematics, you know physics and coding skills, and then you have a good kind of drive to make things like get your hands dirty, and then work with humans and understand humans and human emotions, feelings, and then the artistic side of human feelings, and then you will have good opportunities, right? So gone are the days that you can just know math, physics, and coding, and then go to a hard robotics company and then survive, right? So in the future, you need the other side, the emotion side also, right? So because these robots will be working with humans, and then the humans should be really integrating with these robots. For that, you need to uh, really respect the human feeling side, right? So which is user experience, and then that kind of things are also important. But at school level, just be aware of that. So this is just to give a brief introduction to the Imperial Robotics Forum. So Imperial Robotics Forum has 44 robotics labs. Um, and then out there, we are organized into 3 major themes like home robotics, health robotics, and infrastructure robotics. And so under each theme, different professors lead each laboratory. My laboratory is one of them, right? So maybe I'm here. And then I am the present chair of this Imperial Robotics Forum for 2 more years. So within the Imperial Robotics Forum, so which is now altogether, we have about current ongoing funding of about 50 million pounds. And then we have had 64 patents and then 16 robotics companies coming out, and then lots of other scientific activities. So just to give a quick run through about SoftRobot laboratories, George Mylin's lab. His lab is working on minimally invasive surgery and especially gastrointestinal surgery. So his robots can go in the gastric tract and then do intestinal observation and surgery. And then he is developing this kind of soft robotic anchoring. So this kind of cylindrical anchors, you can go in the intestine or gastric tract, mostly the intestine, and then so inflate this anchor and then latch onto the inner surface of the intestine, and then the robot can go through that anchor and then do the surgery. Ferdinando Biena, Professor Ferdinando's lab, his lab is working on in a mosquito needle inspired robots for brain surgery. So you know, if you send a robot through the brain to do let's say a tumor surgery or something, it can damage healthy tissue, right? So his approach is like, so you know, the mosquitoes can kind of sting, and then it goes through your skin, but it doesn't damage the skin, right? So you can pull out its sting, and then you won't see an injury. You will just see blood coming out. So this same idea. So it has like a, you know, 3 bevels, and then they just slide on top of each other, and then that is how it manages to send such a very soft, tiny needle through your very hard to punch skin and still get to the blood layer, right? And this kind of robots are really good for brain surgery. Mirko Kovács lab, his is working on bee-inspired insect robots for mostly for infrastructure monitoring, and yeah, so like, you know, working even in the wild. White He's lab, he's working on dragonfly-inspired robots and dragonfly vision systems. Etienne Burdet's lab is human-robot interaction. Nicholas Rojas lab working on very metamorphic, or we call it malleable robots for grasping, and then this is especially applicable to companies like Amazon, and then he has a strong collaboration with Amazon. And I think Ocado, I don't know very much, but Amazon definitely. For you know, object handling and packing, right? My lab, Thrish lab, called the Morph lab, is working on soft robotic grasping and haptic perception. Soft robots are used in industry heavily now, for especially for food handling, and then industries with, like, you know, objects of very odd shapes, right? So that cannot be really calibrated, and then so the soft robots' advantage is like, so they can just wrap around these objects, and you don't have to have a huge plan or a calibration or a very complicated program to handle these things. For example, this robot, so it is just a sack of you know, granules, and it is just a soft sack of granules. You can push against an object, so this passively just wraps around that object. Then you suck the air out, and then that kind of freezes that shape, and then that is your grip, right? So this is one example, the mighty robotic fish. This robot is tethered and remote controlled. Just to be clear, it is not fully autonomous, and So these kind of robots can be used for underwater resource monitoring or pollution monitoring. So this kind of robots can be used, I think, in Sri Lanka even for underwater tourism and promoting all this, taking the nice videos underwater to promote tourism, and then to monitor your underwater resources like seaweed, and even helping the fishermen to locate fish. I don't know. There's lots of things you can do with this kind of robots, soft robots. Okay, so this is my some of the work my lab does. So this is Xian Tang, my PhD student who graduated a couple of months ago. Now he's assistant professor in the National Chao Chung University in Shanghai. And then his work was a collaboration with Suzhou Central Hospital in Suzhou. This is the northern part of China. So we went to this hospital, and then they have so many farmers come into the hospital with wrist injuries, right? So they do this kind of orthosis to restrict the wrist. And then, but when the farmers or these people, the patients go home, sometimes they develop pressure points, right? So that is very uncomfortable. So because the skin grows and then the hand, the fat layers grow, but the orthosis remains the same, and then that creates these pressure points. So these are really uncomfortable if it is, especially if it is several weeks of wearing, right? So the idea was to develop a soft sensor skin underneath, and then the soft sensor skin can monitor this kind of pressure point developments. And then we had designed it so that the sensors are located in the most statistically highest pressure point development areas under the hand. So we took data from patients, and then we did a lot of complicated steps going to this point, and then we developed this special soft sensor. And then you might wonder why these shapes. So these shapes are for a purpose. So we did some finite element analysis to see how the shear forces, that is the like stretching forces between the orthosis and the skin. Like, so when you kind of rub against each other, they can give you false alarms, right? So because the sensor has a reading. So to minimize that kind of false alarms, you can have this kind of fish scale inspired uh, pattern around it. So it starts small and then grows bigger, and then that way that kind of external noises can be limited to the periphery of the sensor, and then the sensor is insulated from that kind of noise. So that way we can make it more robust, right? So the idea is then we have this sensor skin under the orthosis, and then this can remotely inform the hospital about the possible pressure point developments of let's say different thousands of patients out there. And then if there is a patient who is undergoing some kind of pain, the hospital knows about it because the sensor is informing the hospital. And then the next step is to remotely send a command signal back to the orthosis, um, where we have a thermal coil, and then because this material is low temperature melting point thermoplastics, you can just warm it up below the like in a comfortable region, not so dangerous to the human skin. The human's skin is about 30, 36, 37 degrees Celsius, and then you can go up to about 40 degrees, 45 degrees without damaging, and then just release that pressure, right? So, but we haven't done that yet, so this is the next step. Okay. So this is Sarah Adela Guman. So she also finished her PhD in my lab. So her work was to understand how mountain goats survive in these mountain cliffs, and then see if we can get some inspiration to develop robots that can help farmers doing farming in this kind of very hilly environments, right? So she is coming from Ecuador, and then she wanted to help Ecuadorian farmers that way. So, but but we just go back to the very fundamentals to understand how this kind of animals survive on those very cliffs. And then the idea was that it may not be the brain which is doing the job, because if you sleep, the signal from the hoof to the brain takes about 120 milliseconds to reach. And any kind of calculations in the brain takes about 50 to 100 milliseconds. And then the brain has to, the primary motor cortex of the brain has to send commands down to the muscle fibers to move. And then those commands take about another 100 to 200 milliseconds to reach and amplify in the fibers to make any movement. Altogether, about 300 millisecond loop is not enough, right? So that is the neuroscientific background of that. And then, so she suspected that it is not the brain or the spinal cord which is doing the job, which is the hoof doing the job, right? So then she did very fundamental studies about, how the hoof might be um, resisting sleep by automatically adjusting itself to the terrain and to make some kind of a, braking, just like how your car would brake, the ABS system would work, right? So the ABS system is like chopping friction. So if you brake your car when you're traveling at low speeds, then the friction can stop the car, right? So this we call Coulomb friction. I don't know if you have studied, like, so just the friction coefficient is enough, right? But if the car is traveling at a high speed, and if you still want to brake, that kind of static friction or this kind of friction coefficient itself is not enough. So you have to do chopping friction, right? So this, like, you have to, like, a clapping kind of friction. So the goat hoof is doing that autonomously because of the kind of how the hoof is organized or evolved in this shape, right? She did mathematical modeling, and then she did very careful motion capturing, and then she fitted her experimental data to mathematical models, and then she proved her theory. So I mean, if you are really interested, you can download the paper from here, IEEE Transaction Robotics, and then read. I don't think it is for you. It was for the students at the school. But the important thing is for you to understand that this kind of even complicated problems, we can take a very mathematical approach to understand them, and then take very carefully calibrated controlled experiments to understand these fundamental principles, and then extend them to a useful robot, right? So just making gadgets is not enough. That is not robotics, right? That is gadgetry. It is not robotics. So robotics is more about advanced robotics is more about understanding natural principles through careful science, and then extending them to useful things, right? So it is not random guesses or just random exploration is not really helpful. Uh, and then again, like, so it is very interesting to notice that when even humans, when they want to break on ice, like for example, you can look at Julia, how she breaks on ice. Like, so the friction coefficient between ice and those blades is fixed, right? So the point is that friction coefficient is not explaining how she is breaking on ice. She is implementing a goat-like hoof with her hip joint, like, just she goes down a little bit with bent knees, and then rotates the hip and then the ankle joint to kind of create a physical shape that looks like a mountain goat hoof, right? And then this is a behavioral implementation of the same thing, and then the right is evolutionary implementation of the same principle. So the principle remains the same, and then there can be multiple different implementations. That is one thing I wanted to highlight. So another PhD student, Elham Hamid, she tried to understand how our knee joint is solving problems. Hoof was solving the problem of slip reduction, and then our knee joint is solving another very complicated problem of a noise reduction, right? So you might have noticed, like, so when you ride a bicycle, and then when you ride it on some kind of a bumpy terrain, like the wild terrain, you wouldn't be seated, right? So you come off the seat and then you ride the bicycle with bent knees, and then your thigh muscles are we call it co-contraction, right? So they pull together, and then implement some kind of a mechanical filter. I don't know if you have studied in the school yet about filters. So filters are things that that can be seen in electronics and mechanics. They just filter out. The name implies they filter out unnecessary noise. So what the brain does is, like, so the brain implements a mechanical filter at the knee joint, so that the knee joint takes care of noise filtering, which is the bumpiness of the terrain is filtered out, so that the brain doesn't have to deal with that, right? So the brain can just keep on riding the bicycle, and then the brain at the same time and the background sets the body to solve very complicated problems of self kind of stabilization, and then that way the brain solves it. So brain is smarter than what we think it is, right? So the brain doesn't, like, stupidly arrogantly ride the bicycle with a seated posture and then deal with that complicated problem of jerky body, and then the whole head is vibrating and jerking, and you cannot do anything with that, enjoy that writing. But the brain is taking very elegant approaches to solve that kind of problems, like delegating some responsibilities to the body to solve the problem, and then brain taking care of more, like, things that are really good for that. So for this kind of things, we have to understand the neuroscientific side, and we have to understand the mechanical side. We have to understand control theory and that kind of. So this robotics is not just like, again, like gadgetry, all right? So making some gadget, put together Arduino with a motor and a wheel. It is good. It is good for a start. But if you want to really go ahead and then do useful things, you should study mathematics, fundamental science and physics. That is really important. Whatever you are studying at school, uh, in your classes, science classes, is very, very important, very useful when you go forward to do useful robotics in the future, right? I'm just showing you these things, like how we do test these things in my laboratory. So we do very, very simple, experimental setups to test these things, right? So I think you may study Newton's laws, right? So the Newton's second law, first law, third law. So these laws, to discover these laws, Newton did very, very simple experiments, right? So he just had a mast, a stopwatch, and a pulley, right? And a table. So, and he discovered the Newton's laws, right? So F equals ma. And then that is used in literally everything now, right? So those equations. So the point is, when you do science, when you do robotics, the important thing is to be able to simplify a complicated problem to the bare minimum, where you can test the basic principle. And if you are discovering a universal principle, that universal principle should be present in the most simplest version, right? Where you can find it. So Newton didn't go to, fire a rocket to understand the third law, right? So he did very simple experiments to understand that. So don't discount the kind of very simple experiments you are doing in the school, in the science lab. That is exactly the mind of a good scientist, right? So, like, you try to simplify those very complicated problems, and then see these things in the simplest form you can find it, and then test these things, right? So in this test, it is just a simple movement, and then we are understanding a very big principle about how the knee joint is working, right? So we are not doing a knee joint, we are not walking. It is just a simple back drivable motor and this plate coming and hitting the leg, right? So this plate is simulating the ground, and then this motor and this system is simulating the leg and then the knee joint. So when I do demonstrations in the lab, like people wonder, like, where is the leg, where the knee joint, where is the ground? We don't have any of that, right? So we just abstract it or simplify it to the most simplest version. Otherwise, there are so many things happening, and then we cannot explain what is causing what, right? So this is just a linear movement, and then that can explain what we want to show. So this is for school children. This is very important. That mindset of simple thinking to understand very complicated things is very important. So another project I'm involved in is this Robo Patient project, which is about a dream of having a robotic patient in the hospital, so that we can project, at least we can use that robotic patient to teach medical students how to examine a patient. And then in the far distant future, we want to project a patient from home to the hospital physically, uh, to the robotic body, right? So you have your human body, and then you are at home, and then you are sick, but you don't want to go to the hospital, and then your physical body can be projected to the robotic body, and then the robotic body will try to camouflage your body, and then present it to doctors, right? So this is kind of inspiration is coming from this octopus. So you can see this octopus, right? So see how it camouflages itself to a, oops, sorry. How do I go back? Right. So see how this octopus is camouflaging itself to a seaweed. It is that octopus, and then within a few seconds, it is becoming a seaweed, right? So see that how that animal could camouflage. So we want to do the same kind of camouflaging in a robotic body, right? So that we are developing these robotic organs that can, you know, change their stiffness, change their shape, create fibrosis conditions, and create cancer conditions, and various types of conditions can be created using a computer algorithm, right? And the idea is in the future to be able to wear some kind of a jacket that scans the human body, and then that sends identify some kind of parameters in the physical body, in the organ conditions, and then project it to the robot in the hospital, so that the GPs or the doctors can examine the robotic body now camouflaging your body, and then make some basic diagnosis first. And then the other advantage of that is, like, your physical medical history can be archived in a physical tangible format, so that when you go from one country to another, you just carry your history of parameters, right? So the bodily parameters, and then any doctor can upload those parameters to a robotic body in the hospital, and then go back and forth your history in few seconds, right? So, like, how your body felt like a month ago can be felt just in a second, right? So because that is physically archived now. So this is a project I'm leading with multiple partners, medical partners in Oxford University Radcliffe Hospital and University of Cambridge, and I'm leading this from Imperial College London. So, and then we are working with GPs and general practitioner trainees these days, for example. Sorry. So this is a GP examining the robotic patient, the current version, and then we are getting feedback from them, how they examine our robotic patient, and then we, monitor how they have fingers. So this is not like simple, like, how they kind of various different types of examination techniques they are using. And then the robot is monitoring how the human is examining, and then that way that archive data can help medical students, right? So because medical students, when they examine, they can compare themselves with how an experienced GP would examine the robotic body, because the robotic body can display how they interact with the robotic patient. So this is one example where we try to get pain expressions given from different ethnic backgrounds, like so black or white or Asian backgrounds, because the same robotic body for the same illness, the pain expression from different ethnic backgrounds can be felt differently by different people based on their ethnic background, right? Or the gender background. So this project is trying to, have a same robotic face that can express pain from a black male or a white male or a white female or Asian male, Asian female. So this the head can go through structural changes to change. Right? So this is a black woman, and then it can transform itself or camouflage itself to different shapes and texture and color of different ethnic groups. The important thing is to give our doctors, medical students, an experience about how different ethnic groups would express the pain in, the same pain in different formats. So to make their observations very robust, right? So these kind of experiments are going on now. This is not a simple task, I would say. So this needs a lot of mathematical analysis of different human faces and then their structures, and then making a robot that can, go from one configuration to another. For example, I don't know if this video has that. No, yeah. So this project whole involved that kind of, making these kind of robots that can camouflage, right? Patients. So I think this has that. Yeah, this video might have that. Like I forgot what video had what. Yeah, I think this video has that. So we take images from different, multiple images from different ethnic backgrounds, and then we calculate some kind of average face, and then we look at some facial parameters called width and kind of the height, and then where the eyebrows are located, things like that, and then we kind of simplify it, boil it down to about 4 important parameters. We call them principal components. Don't worry about it. So the 4 principal shapes that really define your facial identity. And then that way we can go from one ethnicity to another. And then the important thing is we know the exact mathematical map from the force you are applying on, let's say, the abdomen, painful area, to the pain level, right? So it remains the same. But when you express that, when you express the same pain level from different ethnic backgrounds, we see that different people understand it in different ways depending on your own history, right? So your gender and your ethnic background. So this is an example of how the robotic face is working, right? From going from one ethnicity to another through a structural transformation, real time. And then it is just driven by motors. You can see, so eyes and nose and mouth and those relative features moving from each other, and then giving to, from one gender to another or ethnicity. And then on top of that, we project this high level information onto that face. And then we create that robotic patient idea. Okay, so I'm not going into too much detail on that. So next, I wanted to talk about how you can think about these things, right? So it's some kind of a format for you to think. So the important first step is to understand the ground level need, right? So you first understand the ground level need. For that, you have to be connected, right? So to the environment, you should be really grounded, like, so you can talk to, in my case, doctors, in your case, it can be farmers, it can be anybody with a problem, right? So they want to solve their problem. And then you want to ask a second question, who will pay for it, right? So whatever you're doing, like, who is going to pay for that, right? So you can make innovations that are not really needed. You innovate, but nobody buys it, right? Then there's no innovation. I mean, you wasted your time, right? So somebody should be prepared to pay for the solution you are developing, right? And then you should look around and then learn lessons from those who have already tried it before, right? So you don't want to make the same mistake again. And then look around and check, who tried it before, and then what what can I learn from them, and what went wrong, and then like that kind of critical, like a learner attitude is very, very important. Keep your student attitude till you die, right? So that's what my advice. You should be a student all the time. So this student attitude is very, very important for any innovator. And then lessons from things that are already being used, right? So there are, let's say, if you want to look at cars, if you want to look at bicycles, if you want to look at something, just look at what is already there, and then how can I make it better, kind of question, right? And then so you should there are maybe like thousands of different things you can do about it, right? So for example, you look at a soft drink, or you look at some meal you are making. Like, let's take like something like, for example, a curry your mom cooks, right? And then you look at that curry and then think about, okay, is there anything I can mm, do to make it better, right? Maybe chopping it a little fine, or adding some onions, more of onions, or more of chili, or more of that, or less of that, something like that. And then you look at what are the critical problems you should be solving. Not everything, right? So you should be solving A, B, and C, not D, right? So because A, B, and C add most value to the solution, right? So you're going to drop few things. And then this way, so this is called a kind of Pareto 80-20 theory. So if you look around in your room, you might notice that 20% of the things in your room have 80% of the value of the room, right? So for example, your computer together with certain things around may have about, those are 20% of the stuff in the room, but they contain 80% of the value of the room. So if you were to protect your room, you should be protecting those 20% of the things which can be protected with ease, without worrying about every little bit in your room, right? So making, developing a solution is the same. That critical problem solving is like focusing on the top 2 or 3 things that will have 80% or more of the value of the solution. And then that way you simplify your life, right? And then still be effective. So you're really focusing on few critical things, and then other people who rush to solve things like might end up struggling because they took the wrong end of the problem. And then focus on those critical things, and then do prototyping, right? So rather than making very complicated prototypes, first do like cardboard prototypes, and make anything out of what you can find at home. Make something and then try how it look like, how will it feel like, how should it look like, and that kind of thing. You can sketch cartoons, and you can make paper things, and those are the things you should be doing first, and then get some feeling out of it, right? And then test it with real people, not just like like abstract thinking. Like, test it with real people, and then go to prototypes. Like, so underneath I have driven circles, right? So you should be circling around, keep thinking, and then walking around like so, everything. And then what really works with people is what works, right? So don't worry too much about what should work. Worry about what works, right? So, and then focus on that. What works is the thing that fits with real people. And then beyond that, if it works out, it's a great idea, but that is not the end of the story. It is just the beginning, right? So if you want to make impact, then you have to have team up, right? So you have to work with tech people, business people, marketing models and growth plans and then financial plans and everything. You cannot do everything on your own. You need a team, right? So this is roughly where Sri Lankans are going wrong, right? So most Sri Lankans think that, okay, I innovated something and then I own this intellectual property, and then yes, that is true, and then I should own everything, the whole business I'm making. It is impossible. And then that is a very, very conservative approach, and then you never make progress beyond that point, right? You should really team up with legal experts, financial experts, people who know about it, marketing experts, and then you listen to people who have done business, right? And then that is how we work, right? So we now kind of have grow the pie, and then we cut a small slice of that pie, rather than having a small pie and then having 100% of that small little pie, right? So we grow the pie, and then we cut a slice which is bigger than that small pie, and then we grow like that, right? So if you can, as students, get this idea really in your mind, that is really helpful. So one example, so when I was in Sri Lanka in 2001, 2002, I went to Jaffna, and then I noticed that there are lots of landmines up in the north, right? So these all this oops. So you can see the Jaffna Peninsula, and then those red dots are where the explosives happened, explosions happened and somebody injured. And then the most explosions or injuries were between 18 and 35 age, and then male farmers, right? And then when the breadwinner, the male, has an injury, and then the females have to struggle a lot because they have to do the fight so many fronts, right? Economic fight, and then the security fight and everything. It's great. So we wanted to do something to contribute to solve this problem of landmine detection. um, and then we went, and the first thing we did was to listen to these people who are really already doing things, right? So this is the top is Halo Trust, and this is Humpty Dumpty, a New York-based NGO, and then this is Ronco, U.S. State Department funded NGO working, and then I'm just showing these NGOs who are doing about 20% of the work, right? So the 80% of the work was done by the Sri Lanka Army. Um, so they did a lot of work, and then they did very, took very careful techniques, and I'm just showing that this is very laborious, right? So what these NGOs are doing. And then I mean this is the lowest technology you can use, the gardening rakes. And then this technology is like metal detectors that gives about 90% false alarms. Every time you get a false alarm, you have to stop and then dig, and then mostly discover that it's a bullet case or a shell fragment or a nail. It is not a landmine, right? So the 90% of the time you're just wasting time, right? So, and then, okay, Ronco was using dogs, which is really great, but these dogs were imported dogs from outside Sri Lanka, and then they, given the climatic conditions, they fall ill, and then when they are, they catch a cold, they had to be laid off for about, a month at least, and then some other people using flails, which is not so good for the terrain, because like, so if you remove the topsoil layer, the next rain can kind of wash out the fertile soil layer, and then you are basically limestone, and then the farmers cannot really return and then do farming on that land because it's just barren land, right? So we wanted to do something slightly different. And then we tried, so the paper cups first, right? So, and then we looked at different animals, like mostly this I was fascinated by this iguana who walks on a landmine field without triggering a single landmine, right? And then we wanted to make a robot that looks like iguana. The first was a paper cup model, and then our robot that is tested in the grounds of University of Moratuwa. And then we trained this mongoose in the Mattegoda camp, the army camp with the Engineers Brigade of Sri Lanka. And then we wanted to, we were successful in this training, so it could finally learn how to sniff for landmines. And then we wanted to guide this mongoose, mongoose in Sinhalese is Mugadia, with this robot, right? So the robot guiding the mongoose in the minefield, and then detect these landmines. And then we developed this kind of robots that can go and brush without managing the brush. As you can see, the robot goes through the brush, and then it doesn't leave a trace. Right? So it is very, very robot kind of brush. And then these robots were made out of rescued kind of recycled material called paper. So the motors were literally wiper motors, and then just recycled material from junkyards. So that was the first kind of recycled robotics in the world, and then that went on. That is another story how we took this approach, which is suited to Sri Lanka. But somehow we published, and then we gave this ideas to collaborate Defense University to continue. But like I left Sri Lanka in 2005, 2006. And then at Harvard, I went to Harvard University, and then at Harvard, I continued this work. And then I met a Sri Lankan student called Lahiru Jayatilaka. So he and I continued to work on this, and then he went on to launch his own company. And then now it is a US-based company, a California-based company, selling these products to United States Army, US Special Operations Command, and then US Army Europe, and Joint Improvised Threat Defeat Organization, GDO. And that company is called Red Lotus, redlotus.com, Red Lotus Technologies, right? It's a very successful company now, providing this equipment to lots of US Army, and I guess other armies in the world, um, and then saving lots of lives in different countries. So the journey from that start, like the visits in Jaffna, and then talking to these people, lots of sleepless nights, and then we were sleeping under stars in Jaffna. Like we didn't have a place to stay, and then sometimes we were sleeping outdoors, and it was beautiful, right? So when you wake up in the middle of the night, you see stars, and then you realize that you were sleeping outdoors, right? And then that was like just before the war erupted again. I really cherish those memories of talking to people in Jaffna, talking to military, talking to these NGOs, and then just be grounded. And then that experience really paid off, right? So, and that is the lesson learned is spend enough time to identify the problem, its political, economic, and social and security dimensions before diving into technical details. And the so-called experts can be misleading sometimes. They have their own fancies, and look at what the user buys in related circumstances and ask why, right? So, and then I must confess that US Army had a very positive attitude compared to several other agencies I have dealt with, and then they were really positive and proactive, and then that is why it worked out in the US, right? Okay. So this is another problem. So this is coconut all over the world. There's an insect called red palm weevil, and this has been declared as a United Nations global threat by the United Nations Food and Agriculture Organization, because this insect damages about 40 palm species, and then the estimated annual loss to growers is 450 million pounds, right? And then which is growing because the market size of coconut production is going to reach about 19 billion pounds annum. And then global palm oil market by 2021, this year, is about $92 billion, right? So this insect causes about 10% of the damage, which is about like $10 billion damage to this industry, and there's no commercial solution to this. And then we went to the farmers, and we talked to them, and then how they identify this insect activity, and then in different parts of the world. And it is very important to talk to them, and then especially in Sri Lanka. So they look at this yellowing of trees, bleeding of trees, and then this kind of things. And then we wanted to develop some kind of solution which is not possible, has not been possible before, right? Because if you look at the sounds of the insect activity, so it is very similar to bees sucking honey, and then water transportation up the cambium of the tree, or twisting of leaves in the breeze. And then it's so difficult. And then we developed a new sensor which is inspired by how the human cochlea works in the ear. And then we developed a mobile phone app, and then that solved the problem, right? So this is the best sensor in the world. And then I spun out a new company called Permear Sensing, and then that company is now selling this all products, and soon this will be available in Sri Lanka. And this is now we are testing with the growers in Mexico, India, Malaysia, Indonesia, Israel, and India, right? So United Arab Emirates and Croatia. So it will come to Sri Lanka at some point. So this can basically boost up about 10% of the Sri Lankan coconut production, and then save money to farmers. So the story behind that is a bigger story. So I'm just the technical side of it, and then there were lots of people who helped us, who are in the board of directors, right? So the business people, the marketing people, legal people, and then all there's lots of different people, and then Imperial College London fully behind it, and then investing money into it, right? So investors. So the point I want to make is like, so you can start with very basic questions, and do the science, and then if it is grounded enough in a real problem, there are lots of very basic scientific questions you have to solve, and then you solve them, the critical bit of the problem, and then you can bring it to an impact, right? So, and then launch your own company. So you typically at Imperial College London, so all professors have, in addition to their professorship, the academic work, we have companies of our own, right? So we are not really worried too much about our retirement or anything. So lots of things are happening on the side, so which is really encouraged, right? So I want to encourage you to do science because of this reason, right? So in the future, you can do science, you can enjoy your life doing science, and then do discoveries and also make money, right? So you shouldn't be a poor guy somewhere, right? So like in Sri Lanka, something lacking is like, people just do the academic stuff, but they really don't go into the impact, right? So then there are people, of course, right? So, but we need more of them, right? So you should drive this, right? So you, unless you're contributing something back to the economy that funded us, that supported the universities, supported the schools, you're not giving anything back to the economy, right? So you have to give something back to the economy, employ people, enjoy making impact of science to the society and make the society a better place. So I conclude with this, and then again congratulate Royal College Science Society for having me, and having doing this event that might be useful to students. Hope it was useful. Thank you. So I can take questions.
Yes, thank you, sir. Just a quick notice for everyone before we head on to the question and answer session. There is a feedback form in the chat, and I request from you that you take a moment of your time to give us your valuable feedback, as it helps us to improve our quality of delivering in the upcoming lectures. ඔබගේ වටිනා අදහස් chat එකේ තියෙන Google form එක හරහා යොමු කරන්න විනාඩියක් ගත කරන ලෙස මා කාරුණිකව ඉල්ලා සිටිනවා. එමගින් අපහට ඉදිරි දේශනවල ගුණාත්මකභාවය තවදුරටත් වැඩි කර ගැනීමට උපකාරයක් වන බැවින්. All right, now I'm sure you all have many questions, which conveniently opens us up to the questions and answers session. You can send your questions on the Zoom chat or send your questions through the live stream chat on YouTube. ඔබට ඇති වූ ප්‍රශ්න Zoom chat එක හරහා හෝ YouTube live stream chat එක හරහා අප වෙත ඉදිරිපත් කරන්න. Sir, we have our first question. Can we build a soft robot at home?
Definitely, yes. Yes, you can make your own soft robot at home. So you just need, I mean, there are soft robots you can make out of clothes, right? So, and then plastics, and you just need, maybe if you want to inflate or actuate something, you can have syringes, right? So just, just a syringe, and then you have water or just air, and then you have some kind of Teflon tubes. And then with that, you can make your own soft robot. So that's a basic version you can make. And then in fact, some students during the COVID lockdown made robots at home. And then we had, this year we had a new theme, recycled robotics, right? So robots for circular economy, basically, in a posh language. But the point is you can make very useful robots from things you just throw away at home.
Okay, thank you, sir. We have our second question as well. Can we make artificial intelligence systems using Arduino?
Yes. I mean, what is artificial intelligence, right? So artificial intelligence is just logic, right? It's like, how you reason, and then your reasoning can be programmed in a simple Arduino code, right? So as far as you have sensors coming in, sensor information, right? So you read something, measure something, and then make some argument about it or reason about it. And then you take action, and then those action can be fed back to your ports, input output ports, and then control something. So there's nothing called artificial intelligence. It is just reasoning.
Okay, thank you, sir. Our next question. What are coding softwares used to give instructions to electronic components?
Sorry, repeat that question.
What are the most commonly used coding softwares to give instructions to electronic equipment? And
I mean, like Python is rapidly taken up. Python is really good. It used to be C, C++, C Sharp. I mean, C Sharp is still very, very popular, but I would say if you are a beginner, start with Python.
Okay, thank you, sir. Our next question. How can we start robotics at this time for beginners?
I think, I don't know what is available in Sri Lanka. So if you can, get hang of an Arduino board or Raspberry Pi board. Now Raspberry Pi 4 is available, which, if you want to do little advanced robotics, you can install ROS, Robot Operating System, in that. And then, so Raspberry Pi, Arduino, or you can buy off-the-shelf robotic carts from RoboShop sometimes, if it is available in Sri Lanka. Just get on with a simple sensor and Arduino program or Raspberry Pi program, and then do something useful. I mean, think about, first it is not the robot which is important, right? So what problem are you solving is the problem, right? So look around, and then at home, is there anything you can do? Maybe you want to develop something, a simple thing like a robot that can go in your garden around 5 p.m. or 6 p.m. It knows the time, and then water your plants, right? So it opens up a tap and then fills a bottle, and then it goes around your garden and then just waters your plants or something like that. A simple thing that is useful, and then make it cool, right? So like impress your mom, impress your family. uh, do something useful first, like, so just doing robotics for the sake of doing it is not really encouraged. um, Try to do something. I mean, it can be cleaning the gutters in your house, right? um, Go to the roof and then do some cleaning. um, yeah, things like that, right? Plumbing. Think of that. So yeah, think of some problem that a thing that is literally dirty, you want to do it, or the time is not right, or maybe you want to do a security robot, like that just goes around your house in the middle of the night when you're asleep. You're just programming it to light up a torch, and then just wave it around, and just to show that people something is monitoring, or have a webcam that monitors, records around your kind of house in the middle of the night for you. That kind of simple things that you can enjoy, do something. Yeah.
Okay, thank you, sir. Our next question. As Sri Lankans, do we have opportunities in the field and future of robotics?
Of course, so Sri Lanka must get on board robotics right now, right? It is, if it, I don't think it is late. As I said, the robotics market is growing at 40%, right? So why, I don't see why anybody wants to ignore that, right? A market that grows at 40% right now, which is entirely your future. Get on board that, right? And then get your skills right. As I said, it is not just gadgetry, right? So just getting Arduino board, yeah, that's great to start, but focusing more on your school science and math you are doing, and then taking it seriously, because without math and science and physics, no knowledge about biology, and some experience about dealing with humans, arts is very important, right? So whatever you are doing at school, like drama, expression, and poetry, all those things are important in robotics, right? So let's say one day you want to make a robot that reads poems to people, elderly people, right? Reads a story to people, elderly people, which may be bored by the people in the future. So there's somebody to talk to, somebody who can express feelings. Those things might be useful, but for that you need to know this human side of things, and then whatever you're studying in the school is going to be very useful.
Okay, thank you, sir. Our next question. Can you give us a brief explanation about self-navigatory vehicles?
Self-navigating vehicles. Self-navigating vehicles are everywhere now. I mean, the good example is the Google car, and then all these autonomous vehicles. Like, so all what they do is, like, so they take lots of measurements about the environment real time. Like, it can be lidar systems, like the laser scanners, and mostly laser scanners right now. uh, and then this take this point cloud information and then making sense out of that rapidly, right? So real time, using a very complicated software programs, and then taking very real time decisions. So the important thing about autonomous navigation is about understanding the environment pretty rapidly, right? So for that, it needs lots of pre-trained models, and then how to understand who a human is, and whether that human is walking towards you, away from you, or whether two humans came together and then they crossed and then they passed, and then whether which man is going which way, whether two men came and went apart, or two men came and then went on opposite directions. Those things are not easy problems, right? So there are lots of laboratories in the world are working to solve that kind of problems. But basically, autonomous navigation is about understanding the environment around you real time, pretty fast, and then taking the right decisions, which is not easy.
Okay, thank you, sir. Our next question. What is the path of becoming a robotics engineer from school to university?
Great question. So at school, you can study anything, right? So most robotics engineers study physics, math, and then in addition, you can do other things, design and technology. You can do chemistry, you can biology, or whatever, depending on the choices you have. But math is the core, right? So that you have to do math. And maybe physics is option, but like physics is a helpful thing to know. Then in the university, you can really literally do anything, right? So you can do civil engineering, chemical engineering, electrical, mechanical. Really, it doesn't really matter. You can do anything. But if you want to do robotics, you have to know something about electronics, something about mechanics, the fundamental principles of mechanics, and as fundamental things about control theory and algebra, calculus and that kind of things. So the math is going to be the backbone again, right? Mathematics is the backbone in robotics, and then around it you need to know mechanics, electronics, computer science, and programming. Efficient programming, we call it real-time computing. Without a lot of overheads in the computers. And if you have that background, and then you need to have some, attitude, right? So roboticist is an attitude where you are a problem solver, and then you should be able to identify some problem and then kind of reduce it to several solutions, and then one of that can be a robotic component, right? And then the rest of the solution you should know, right? So I can have a robotic solution, but for it to work, I had to have these other solutions coming from, user experience designers, other people, right? And then be able to work with these people with respect, right? So you should know that the robot is not going to solve the entire problem, right? It is solving maybe 20% of the problem. And then you have to have respect for other people who are solving rest of the problem, right? And then, it can be finance guys, it can be marketing guys, it can be biologist, chemistry, psychologist. Like, so for example, in that Robo Patient project I mentioned, I had to work with psychologists, right? So the psychologists and general practitioners, medics, without them, my robot is nothing, right? So that is very, very important. So I should know, I should be humble enough to know that mine is just a small piece of this big puzzle, right? And then that demining robot, without the army, I cannot do anything, right? So their input, their experience, that is really important. And then you have to have respect for that. And then the red palm weevil insect detection sensor, I had to have respect for the growers, right? Learn from them, and the farmers who are giving us feedback from different cultures, different countries, and then solve the bit that is really needed and then can be solved using the best robotic practices. So that is an attitude that is really needed, which is, you will learn it in the university, right? So you need that. And then from childhood, I would say, if you want to be successful in the future, don't be a lonely player, right? So be a team player, right? So know that as a single individual, you are a speck of dust in this world, right? So you are nothing. You are nothing as an individual. You become a powerful person in a team, in a pack, right? So if the pack is powerful, you are powerful, right? So that is how we work. So I think something the Sri Lankans can learn. It's like, have that team attitude, right? You don't care whether my team members are Tamil, Muslims, or that crap is not really good thinking, right? So I don't care whether they are coming from a Buddhist background or a Christian background, Catholic. I really don't care about that, right? So what is important is their skills, right? So I need a marketing guy, I need a finance guy, I need a biology guy, I need a GP, I need a farmer here, I need a military guy or whatever, right? So, and then for my piece to be successful, and then don't question their backgrounds. Like that's the first thing, uh, very important, right? So, I mean, if I can ever give an advice to Sri Lankan students, don't put other things that are really not important to the front, right? So the skills should be at the front, and then your team is the skill set. Yeah, that is how you become successful.
Okay, thank you, sir. We move on to our final two questions of this afternoon. Could robotics be a threat in the future?
Yes, it can be a threat in the future, a big threat in the future, unless we don't manage it, right? So we had to be. That is why I said the human side is important. You had to really be thinking about how this is going to affect humans, right? How are the humans produced? So going back to the original origins of robotics, right? So we came up with this whole idea of a robot from slavery, right? So our dark, real bad past of the human mankind, how they solved the economic problem at that time, and then we have a different way of solving the economic problem. But the economic problem and then the forces of market forces are going to flow in the future, right? So if they are not really managed, they can be damaging, or they can be a threat to us again, right? So the global warming is real, and then it is coming out of the way we are solving the economic problem, right? So how we are managing the market forces, right? So the way we are kind of bad energy sources we are using, right? So coal power, very dirty energy sources we are using, right? We are killing the climate, we are killing the planet, and then if we are not careful, they can kill us in the future, right? So robotics is the same. So if you don't manage it, if you don't really pay attention to the important things to the mankind, robots that we designed with the purpose of helping humans can end up killing us, right? I'm telling it very upfront.
Okay, thank you, sir. Sir, before we leave, do you have any final words of advice you would like to leave our students with?
I think the repeating thing I want to say is like be a problem solver, right? So like if you see a problem in the society, that is a gold mine, right? Lots of people say, oh, that problem, this problem, this problem. All these problems are man-made problems, right? And then if it is man-made, there should be a man-made solution, right? Okay, so it's like any problem you see in the society, view it as a minefield, a gold mine, and an opportunity, right? Okay, so I see this, let's say some problem with traffic in your city, right? So that is a problem, right? But then think about, okay, what can I do to solve it, right? What can we do to solve it? Then you realize, immediately you realize you cannot solve it on your own. You need a team to solve it. You have to get civil engineers, you have to get sociologists, you have to get different types of engineers, maybe who can design roundabouts, who can design traffic lights. Maybe you need a roboticist who can contribute a robotic drone to monitor traffic, and then make predictions about those sensors and cameras, people, image processing guys. Then sit down with them and then talk in one place, and then what can we bring from our expertise to solve it. So without that, you can just be spending your life complaining about problems without solving a single problem in your life, right? Because you cannot solve problems on your own. As a single individual, it is a problem. But when you get together, it is a solution, right? So at school, try to do these exercises, like, pick some small problems you can solve and then solve them in teams. That's my biggest advice. I guarantee you, your employability, you just go and tell that story in an interview to anybody, you will be the first people to be hired, right? If you just boast about your individual capability, nobody cares you. Nobody cares you, because there's nothing called individual capability, right? So my individual capability is a speck of dust, nothing beyond, is completely nothing, unless I work with people, right? So you should be a good diplomat. You should respect other people, diversity of views, and learn, have this student attitude of learning from other people, and then do teamwork, and a problem solver, not a problem complainer, right? Never complain about problems. Just think about how to solve them. That's my advice. And then I think it's already, at Royal College. Royal College is not my school. I should say that I'm from Richmond College, Goal. But I have huge respect for Royal College, because Royal College has traditionally, given lots of leaders to Sri Lanka, right? So you can sportsmen, political leaders. I think there's something really good going on at Royal College. It is training team workers, right? So and giving right attitudes to students. And then this workshop itself, like, so you're opening it up to other schools also, right? Is that right, Dula?
Yes,
Right?
sir.
So that is leadership. That is leadership. You are not just confining it to Royal College students. It is open to other students also. That is the way Sri Lanka should go forward, right? So that is why I, as a Richmondite from Goal, I have huge respect for Royal College for that reason. So continue that and keep it up.
Okay, thank you, sir. On that note, ladies and gentlemen, that was Professor Thrishantha Nanayakkara, and that concludes this lecture and SCI-NEXUS. It really was a very, very valuable and informative lecture, and I hope you gained as much value as I did. This being the final lecture of this series, I feel the need to request a big round of applause for our lecturer, as well as the Royal College Science Association, for organizing this event for the betterment of the entire student populace that joined with us in the past few weeks, to build your knowledge and interest in different fields in the scientific discipline, and to help you with your future career as a citizen of the world. With that being said, I am Dulwan from the Media Unit of Royal College, and I hope you have a great day.
Thank you very much.